So my talk is on detecting causality with conjugation quandles, otherwise known as non-affine Alexander quandles. And I was able to find that conjugation quandles are able to detect causality in a 2+1 dimensional globally hyperbolic spacetime. So what are knots and links? Knots are embeddings of circles into 3D space, and links are just knots linked together. The simplest knot is the trivial knot, and the simplest link is the trivial link, which are just circles in space. So knots remain unchanged under Reidemeister moves and ambient isotopy. So there's three types of Reidemeister moves: the twist, the poke, and the slide, in which if you perform any of these moves, the knot does not change, it remains the same knot. And ambient isotopy just means like moving one strand over to the left or moving it over to the right without like cutting it open, basically. So knot invariants are basically things that can differentiate knots, but they don't always do that. So knots are different if their knots invariant are different, but the same invariant does not mean the same knot. So like if I had a knot where the invariant was the same, I don't know if those two knots are the same because they might be different. These knot invariants do not change under Reidemeister moves because if they did, then they wouldn't work. And some examples of knot invariants include the crossing number tricolorability, the Alexander-Conway polynomial, and the Jones polynomial. The subject that we are exploring in this presentation is that the number of quandle homomorphisms is also a knot invariant. So the space of light rays in a 2+1 dimensional globally hyperbolic spacetime can be modeled by a torus, as we discussed in the previous lectures. And if two events are considered and their skies are two disjoint circles in the torus.
You may want to say what a sky is, just in case.
Oh yeah, so the sky is basically like if it's like the sphere of what can see the event. So like if I'm standing outside of a certain radius from the event, in 1 second, I might not be able to see the event. In 2 seconds, I might be able to, because this information travels at the speed of light, and you cannot exceed the speed of light if I'm standing sufficiently far enough away. And that's basically what a sky is. And if they
So a sky is a sphere of light rays through the point in the space of all light rays, right?
yeah. Uh, and they form two disjoint circles in the torus. And if the two circles form a trivial link, then the points PQ are not causally related. And if the two circles are non-trivially linked, then the events are causally related. This correspondence between linking of skies and causal relation is part of low conjecture. So as we can see in this picture, this is basically what a trivially linked, trivially linked events look like inside the torus, and it can be transferred into a knot projection on. Oh, okay. And it can be transferred. Hello. And it can be transferred into the two-dimensional plane as a knot projection, which then we can use classical knot invariants to distinguish between knots projections. Okay. Now we can go to the next slide, which is detecting causality. So if a two-sky link is found to be different from the connected sum of the Hopf links, then it can detect causality, since the only link that is non-causal is the trivial link over here, or technically, if we're looking at the projection, it's this one. It's the trivial link within the torus, which corresponds to the connected sum of the Hopf links. So For most links in a 2 plus 1 dimensional globally hyperbolic spacetime, the Alexander-Conway polynomial is sufficient to distinguish causality. However, for the series of Allen-Swenberg links, the first of which is this one, they are conjectured to be valid mappings, and the Alexander-Conway polynomial does not detect causality, which means that we must turn to other invariants. So quandles are these other invariants that we're going to turn to. And a quandle is defined with a binary operation that satisfies the three axioms of idempotency, the existence of the right inverse, and self-distributivity, which is like, so I have these all here, which is the quandle operation is denoted by a rightward facing triangle. So for all x triangle x, it equals x, and that's the idempotency um, axiom. And then there also exists a right inverse, such as for elements x and y in x, there exists some element z, such as x equals y triangle z. And for self-distributivity, it's x triangle y triangle z is equal to x triangle z triangle y triangle z. And these quandle homomorphisms, this is just basically the operations that the homomorphisms go by, and these quandle homomorphisms are not invariants that do not change under Reidemeister moves. So in these quandles are not technically, you can't really like use a quandle homomorphism as a not invariant, but what you can do is count up the number of quandle homomorphisms, and that's called the quandle coloring invariant. So first, we're going to explore how we can color a knot with a quandle. So the fundamental quandle, which is considered a complete knot invariant, meaning it can classify between all types of knots, is too big compute. However, we can map each crossing in the knot as these two operations, where this one is x triangle x and y is x triangle y when it's going to the left, and it's if it's x and y going this way with the y strand going over, it's x triangle -1y. So from here, we can use our other quandles to correspond to the system of mappings. So the valid mappings for the quandle, the valid mappings for example, for the trefoil is that C1 is x1 and x2 going in, and it corresponds to the x3 that's coming out. So for example, C1, we have the x2 going in, and the x triangle y, which is x3 coming out. And then each set of valid colorings or mappings of numbers to each of the arcs through the equations of the crossings is called a quandle homomorphism. The number of quandle homomorphisms that are valid is called the quandle counting invariant. Using this invariant, we can compare the Allen-Swenberg link to the connected sum of the two Hopf links. So what this means is, like, if I have, for example, if I find that there's 3 valid colorings for the connected sum of the Hopf links, and I find that there's 6 valid colorings for the Allen-Swenberg link, then we can say that these two links are different because quandles are not invariants. And then the enhanced quandle counting polynomial is a more advanced form of the quandle coloring invariant. Hello. So, and then the enhanced quandle counting polynomial is a more advanced form of the quandle counting invariant. And it actually takes account, and based on how many counts there are for each number of colors, it forms it into a polynomial, which is like if it was 6x to the third, that means there would be 6 colorings in which 3 colors are used. Now, the focus of this paper is the conjugation quandle. And a conjugation quandle is defined as a triangle B equals B negative 1 AB over some group G. And if we calculate this operation by generating a Cayley table for the group G, and we pick a starting point and we see if the expression B negative 1AB holds for all the crossings in the knot. And if it does, then that coloring is considered valid, and we have to look at all the other combinations that are possible for this group and see which ones are valid. And for example, for the dihedral group D3, the Quandle counting polynomial for the connected sum of the Hopf links is 6q to the third, 36q squared, and 6q, which is which this in order to interpret this, it's you have 6 colorings in which 3 colors are used, you have 36 in which 2 colors are used, and you have 6 in which 1 color is used, which means for the Cayley table, 6 of them have 3 elements from the Cayley table, 36 of them have 2 elements, and another 6 of them have 1 element. And there is one caveat, though. There is a problem when trying to find the number of valid colorings for the Allen-Swinburne link, since it's very, very large. In fact, if we tried to just use this method and brute force all the combinations for the Allen-Swinburne link, we'd have 6 to the 45th combinations, which is way too large. So what we first must do is we must divide the link into portions, calculate the valid colorings across each of those portions individually. And then we have to join the portions together and find the matching intersections. And if the intersections do match, then these are considered valid colorings. So you have to split it into parts, match them together, and the ones that do match together are considered valid colorings. And then, so what we did is when calculated in Wolfram, we find that every group that is smaller than D5 does not work. So later, I even calculated the quaternion group Q8, which is one of the smaller non-abelian groups. And I found that it could not detect causality, which means that every group that is smaller than D5 cannot detect causality. And most groups that are larger, with the exception of D9, the conjugation cannot distinguish between the connected sum of the Hopf links and the Allen-Swinburne links. However, D5 can distinguish using the Quandle coloring invariant alone. Which means, according to this, D5 is the most efficient way to use the conjugation quandle to determine causality. Well, to determine that there's a difference between the connected sum of the Hopf links and the Allen-Swinburne link. And we can see the results here. There's 160 there's 160 different homomorphisms for the connected sum, and there's 200 different homomorphisms for the Allen-Swinburne link. So our goal isn't just to prove that the first Allen-Swinburne link can be distinguished from the connected sum of the Hopf links. We want to prove that for the entire series of the Allen-Swinburne links, which are conjectured to detect causality, can be distinguished from the connected sum of the Hopf links. So what I did is I also, just to make sure that I also calculated the results for D5. And I noticed a very interesting thing. So I also calculated the results for D5 for the second Allen-Swinburne link, and I noticed a very interesting thing. So here, when we look at it, it's 20q to the 8th plus 20q to the 6th plus 60q to the 3rd plus 90q squared plus 10q for the first Allen-Swinburne link. But for the second one, it used less colorings, which is 20q to the 7th plus 20q to the 5th plus 60q to the third, but it did have the same ones over here. So I'm not sure why that happens. So I came up with maybe an explanation for why it does. So, as I said, in order to prove causality, we must not only determine that the first Alan Swenberg and the first Alan Swenberg link and the connected sum of the Hopf links are different. We must determine that all Alan Swenberg links and the connected sum of the Hopf links are different. So, in order to generate a new Alan Swenberg link, this is what happens. So you can see it's basically split in half with the first Alan Swenberg link. With the first Alan Swenberg link being just a half of the second Alan Swenberg link, which is this half. So in order to generate new Alan Swenberg links, we can just say that C1 are like the two sections of the braids coming down. Well, each section C are the two sections of the braid coming down, which is like this section. This would be counted as C1 and C2. So in order to generate this infinite series of Alan Swenberg links, you can just basically copy C1, copy C2, C1 again, and then you just number it C1, C2, C3, and so on and so forth until however many there are, right? And then, so what we wanted to prove is that for every F1 in the number of homomorphisms, there exists another coloring where F1 equals F2, or a parity case where they switch the number of colors used. What does that mean? So basically for every coloring in the first Alan Swenberg link, there is that coloring in the second Alan Swenberg link, or there's a parity case. So Jane in his paper proved that there is a valid coloring in between crossing the C1 and C2. My goal is to prove that there can also be a parity case for which 20q to the 8 and 20q to the 7 both exist in C1 and C2, but they still have to, that is instead of the F1 equals F2, there's also a parity case. So here, if we draw the first Alan Swenberg link as such, we can, and follow the rules for coloring, we can see that we need 1, 2, 3, 4 colors to color this entire thing. So where the red goes into the crossing and the red comes out on this side, but when the blue goes into the crossing, there's a different coloring that comes out on this side. However, for the second Alan Swenberg link, we can see that you can color it by using only 3, which the C still generates a red from a red and a blue from a green, but X for the loop which goes across the two, it can switch colors because there's different colors going into the loop, which can explain why we have this difference between the two counting polynomials. From Q8 to Q7, we have, which remember, these are the number of colors. So if we model it like this, we have 4 colors in this one and 3 colors in the second Alan Swenberg link. So this, here there are, well, yeah, here there are 6 and 8 colorings in L1, and then that becomes 5 and 7 in that second Alan Swenberg link due to the parity case, which means that the odd links of the infinite series will have the same parity, while the even ones will have the same parity as well. And then since also Jane proved that you can't, yeah.
No, no, I just wanted to say that I was very impressed by this because this is very, very different from what I usually Jane had. Like in his case, the colorings were constant, so this was what was distinguishing them all. And in your case, you had really to look at the difference between odd and even Allen-Svanberg links. So this was surprising. Thank
Thank,
you.
thank you. So, yeah, so, but I still needed to use, I still needed to use, I used Jane's, result because I still needed to prove that since for I have 160 here, I have 160 for the connected sum and I have 200 for the Allen-Swanberg. So I still needed to use his result, which says that for every coloring, there exists a coloring in F2, which means that it has to be greater than either greater than or equal to 200 because in my case I ran into the parity case, but that's still the same number of homomorphisms. It's just a different counting polynomial. And Jane proved the first part, so I proved that the conjugation quandle across D5 can distinguish between all the Allen-Swanberg links and the connected sum of the trefoils, which means, importantly, we conjecture that the collection of all conjugation quandles over all dihedral groups is able to detect causality across a 2+1 globally hyperbolic spacetimes when coupled with the Alexander-Conway polynomial. Thank you very much.